Status. Yep. Toby, do you want to introduce the speaker or do you want me to do it?
I'll introduce Sebastian.
Okay.
No problem.
Hey, Toby.
Oh, hi, Sebastian.
There you are.
Am I late? I hope I'm.
No, you're not late. You're exactly on time.
Good.
Now you realize that this is all being streamed to YouTube live, and also there'll be a recording of it later.
I see. Okay. So this is so you're streaming that to YouTube and also recording there?
Yeah.
Okay.
It's part of the workshop. Is that okay with you? We don't have to do it.
Yeah, no, that's fine with me.
Okay. It's useful for people that watch it later on.
Sure.
It's nice to meet you, Sebastian. I'm Emery. Actually, as of a few days ago, I'm a colleague now.
Your colleague, you're saying?
A new colleague.
Okay.
At RWTH, yeah.
Yeah, his network is not working well right now. I think
In the electrical engineering department.
Is that on my side with the network? I guess not.
No, it's Emre's Wi-Fi or whatever is not working properly. But he's a new colleague who moved now from UC Irvine to Aachen and has just joined your faculty literally like a few weeks ago, right? But he was a PhD student with us in Zurich with Giacomo Indiveri, and then he went and got a professor job in Irvine, and now he got a chance to get a job back in Aachen. He's German originally.
Oh, that's great. Then we hopefully get a chance to meet each other soon in Aachen. Then. So is that
Emre, your audio is really not working.
It looks like you're doing really cool stuff. So.
Okay, that's gonna be a problem if I'm the host. Is this any better?
No, you've got serious delays. There's some problem with your network, I think. You're very choppy.
Right.
Are you using Wi-Fi or Ethernet?
I'm using Wi-Fi, but where I am, I have no choice for the moment. I'm gonna try to change rooms.
Yeah, it's congested. Doesn't matter. I better put up the program for the day before we get things going. You can try beaming your stuff. Basically, you have control, Sebastian. As long as you're showing stuff, nobody else can show things on the screen.
Okay, should I try to share my screen then? Slides?
If you want, yeah.
Yeah, just to quickly check.
And by the way, if you have video to share, I recommend you just turn on video sharing and sound sharing if you have some video to show.
I do have video. So you mean
yeah, before you share the screen, choose a video optimized. Makes the videos much more smoother.
But then, so like if I go, I have video optimization on now, but
it's fine.
If that is on, aren't the slides then bad, or is it fine?
No, they're a little bit blurry, but we might like to have video better, right? It's a little bit blurry, but you can still see it. It's fine. And I told everybody you'd keep it maximum 30 minutes, preferably even less, right? So you have a lot of room for discussion of the ideas with the people working on the topic area.
Yeah, that sounds sure.
So that's the idea.
I think it should be less than 30 minutes, and then we can discuss about it. So
yeah, you don't need to give much background. You just need to show what the stuff you've done.
Yeah,
you don't need this kind of background, right? Everybody knows that we can't do this.
Yeah, I mean, I was going to give my perspective on like where I see the challenges, and then show what we've done.
Okay. Good. Thank you.
Am I any better, Toby? No, still dealing.
It's no better. No. I better put up the schedule for today.
Unfortunately, I have no other alternative for the moment.
Okay.
Toby, look at my shirt. Oops.
I can't.
You can. I need to play it's true. Oops.
Oh, he has his Neuromorphic T-shirt from July 4th parade last year, or 2 years ago now.
2 years ago, yes. Like
been through the laundry for years. Sebastian doesn't know that every year down in this town behind me here, we take part in the July 4th parade, the Independence Day parade, and we buy a bunch of these cheap T-shirts and paint them up with designs. And we formed some kind of a dance. Like one year we were a retina, bunch of rods and cones communicating to the cortex. Another year we were dragonfly eye. I can't remember all the different things we were. We always like to make robots out of cardboard boxes, and everybody has a different robot outfit. Usually very uncomfortable.
I see.
And then the town looks at us with some stupefaction, right? They don't kind of understand, who are these crazy scientists, rockets. The parade marshal always calls us, the crazy rocket scientists from the neuromorphs. They don't know anything about what we're doing, but they just like to see these scientists, shoot water on us. It's really fun, Sebastian. You should really come one year to Telluride.
And we also win. We also usually win. They figure out, they always give us a prize. They figure out
either first or usually second or third place prize. Right?
They make up something, so we always get a prize.
Like E for effort. E for effort.
Yeah.
And Andreas is a fantastic ambassador to the town because he fearlessly engages with everybody, right?
Yeah,
he's just always going around and talking to people. And so we got, over the years now, we got to know people in the hardware store and the Elks Club and the bar. We got to know a few people around town.
You're well known over there.
Yeah, we're
this is really very strange. It's happening this year. Toby, and everybody else that, Brown Dog is closed. They cannot find enough people to really serve food.
Yeah, and Andreas is there in Telluride right now.
Yeah.
After July 4th, the town emptied out.
Yeah.
Apparently.
Did any places actually close down?
Emery, your connection is not good.
Poor Emery is suffering from a bad internet connection.
I know. Yeah.
So here we are, Wednesday.
Maybe without video, it works a little bit better. That's right.
Oh, yeah,
Yes,
that
without
is
video
better.
is better.
What were you asking, Emery?
I was asking if any place actually closed in Telluride that we know, like the ghost town or.
There's been, so they are still open, but they're all hit by really strong labor shortages. So Ghost Town's been closing early, but they're still open. I think all of all of the favorites that we would have spent a lot of time in are still there. They're just overwhelmed is really where it is right now.
Oh, okay. So it's the labor shortage and not man shortage.
No, it is labor shortage because the rich people have come and bought every place that would have housed workers, and there's no.
Yeah, and getting to town is like a 2-hour commute every day, right? Coming from Montrose or someplace far away, it's terrible. Yeah, they can't afford to live there. That's a problem with closing off development, right?
Yeah.
Yeah,
But
actually,
they're trying to do something now there.
this is also a problem across all of Colorado right now. There's a massive hospitality industry shortage post-pandemic, including even in the big cities and whatnot. So we will keep working with the town to find best solutions we can. But yeah, it feels unusual for sure to be in town and to realize that we might need to go down and put in some time at Ghost Town to help out next time we're here.
Okay, so I think we should get going, right? So we stay on schedule. So Emre, you're the host of the day today. Do you want to say something about the schedule?
That's right. How's my lag? When did you hear this?
I hear you.
It's good. Your lag is good. We can hear you.
Okay. Okay. But it's like so interactive. Okay, so hello everybody. So this is Wednesday, second week of Telluride. I'm going to be your host. My name is Emery Nefchi. You can't see me because I have a pretty bad internet connection. I apologize for that. So this morning we're going to morning or afternoon for some, including myself. We're going to have first the LTC group. We're going to have a invited talk from colleague Sebastian Trimpe. I hope I got that right, who's going to talk to us about lessons from machine learning for control. I'm really looking forward for that talk. But I guess, Toby, you're going to introduce the speaker. And so I'll give you the stage for that.
Okay, and then following that, there'll be only topic area update meetings, and there'll be a tutorial.
No, we haven't talked, Toby. We haven't talked from the ethics person.
Where is it on the schedule? I don't see it here.
Had update meeting. I think, yeah, already Cornelia gave a.
Okay, could you try to add that to the schedule, please? Because I don't see it on the calendar.
No, TAD, update meeting. TAD at 10 o'clock.
Oh, I see. There's nothing on the calendar.
I know,
so
but
you better announce what it is, Andreas, who it is.
Yeah, no,
right
but
now.
I thought Cornelia did.
No, there's no announcement, at least.
Okay, I think this is really we are confused.
Well, we do have a speaker for the TAD, right?
Right, the speaker.
All right, so can I find that?
Okay, let's
just everybody look at the TAD discussion group for the details about that presentation.
Yes, I think let me find out.
Now, I won't say anything more about Sebastian because he'll introduce himself. If you're interested in what the work that their group doing, take a look at the link to him and also at least to his page, I guess. I hope I got the right page, Sebastian. And you can look also at the recent papers that they publish in this area. I met Sebastian because of I can't remember now, because of our interest in machine learning control, and he was suggested particularly by Manfred Marari. And so I'm glad to hear about this. Cool. We had a virtual visit to his lab, and I thought the work that we're doing was just fit right into what we wanted to do. So Sebastian, the floor is yours.
Yeah, thanks a lot, Toby. Thanks a lot for having me, and very happy to present at your workshop. So my talk is titled "Lessons from Using Machine Learning for Control." So for a number of years now, we've been working at this intersection of machine learning and control. So I thought what I'll do for this talk, and it's going to be less than 30 minutes or so, and then we can have discussion after. But what I thought I'll do, I'll give a little bit, first of all, my perspective on where do I see like the big challenges that we are facing when we combine machine learning and control, and like what are maybe special challenges that are different from general machine learning, and then also show you a few examples, including some videos about kind of what we've done and what can be done. All right. So yeah, let me start just in general. So we all know these great success stories of using AI and machine learning, and obviously this is, for example, this is a decision problem. So in some sense, it is close to control, but in another sense that I'll talk about, it's also very different from what we talk about when we mean control of physical systems in particular. So this is a success story of AI and machine learning. There's many more success stories of AI and machine learning. So here's one from my former home in Tübingen, where researchers have trained deep networks to imitate artists. So you can upload your favorite picture, this postcard image of Tübingen, and then you can choose the artist, and you get back maybe this image in the Van Gogh style. So these are clearly fascinating examples of what we can do with machine learning and AI. But then there's other things that we can't do. So let me optimize here for video. So hopefully you can see this video. So I guess you all know, I mean, these are kind of the type of things we would really like to be able to learn and do with machines, but we can't really do them. On the other hand, humans can obviously learn and acquire these skills. So that raises the question, like where does why do we see this difference? Why do we, on the one hand, have fascinating success stories of AI and machine learning over here, like beating the best human in a complex game like the game of Go, but on the other hand, we still don't have the robot in our households. And one very clear difference that we see here is that the robot is interacting with the physical world. So we perceive the world, and the robot acts in the world. So the system really is in the physical world and has to deal and has to do something there. And that's very different from this one here, because here the system is really in an artificial world, not acting in the physical world. And this also kind of shows the intimate connection between machine learning and control that we are facing when we want to put machine learning on the physical machines, because this is nothing but a control loop. So clearly, control dynamic systems are coupled here with the machine learning. And the big difference is that on the right side, we need to take, or we want to take action in the physical world, while on the left side, this is really an artificial or a virtual world. And this now, if we want to do this, so basically we have a number of challenges that we face when basically learning in the real world. And from my perspective, these are some of the really main or fundamental challenges. So one is basically the way we do. Excuse me. Okay, there was a.
Go ahead. Yeah.
It's okay. Fine. All right. So there's a couple of challenges that we're really facing when we learn the physical world, and one of this is really like how we do sampling. So on in the artificial and virtual worlds, we can essentially sample as much as we want. We can try out arbitrary behavior, and this way generate lots of data and learn from it. And this is obviously not possible for our robot here, because this one doing one wrong move could already mean the system is destroyed, or even worse, someone getting injured. So really, the way we do sampling is much more constrained. It's constrained by the physics, and also it's more costly in general. So we have to live with smaller sample sizes. And then often, sort of the machines that we want to learn with, they are not there primarily or only for learning. They are there to do something else. Like a production machine is there to produce some parts or so. And on parallel, we would like to learn. And this brings about some interesting conflicts between, what do we need to do to learn, like excite the system, for instance, versus what do we want to achieve in terms of, our normal operation of the system. And then often also, we're not just facing just one problem, but if you think about multiple robots in a production plant or multiple cars or something, you have multiple systems that interact, and all of them solving learning problems. And then finally, last not least, is that these systems are in the real world. So we better have an idea of whether they work or not, also what their limitations are, and kind of we'd like to be able to give guarantees. And these challenges that are listed here, in my opinion, are like some core fundamental challenges that we have when we combine machine learning with control, or machine learning with the physical world, that we don't necessarily have when we talk about machine learning only. Like, for instance, these aspects here, like robustness, stability, and so, is something that we always deal with in control, but that is not usually a concern if we just talk about standard machine learning. So these are challenges, fundamental challenges at the intersection of data science and engineering, or more specifically between machine learning and control. Now, these challenges are also those that we're trying to deal with when in our work. So what I want to do now is kind of present you a few examples of what we have been working on, and some of the things that we have been able to achieve, as it may be a basis for further discussion then. So one problem that we're looking at a lot is kind of the question of how can we learn feedback controllers automatically from data, and in particular from small data, because already mentioned, like sampling on the physical platform is often involved. So we want to be very efficient, sample efficient there, and also be able to learn from small data. And one aspect, or also one thing, one approach that in my opinion works very well and has worked very well in a couple of examples, is if we combine, our understanding of what are good controller architectures, then with basically the data-based, the machine learning-based approaches to optimize those. So here's just basically a very standard pipeline where we have some sort of control design, could be PID, could be AQR, what have you. And this gives you essentially like a controller architecture or controller that however has open parameters theta. And these parameters critically determine like how well is your controller doing. And then and they will critically determine how well you're doing on the physical system. And what very often in real life, what we do is we design a controller, and then we put it on our hardware, and then we try it out. And then this robot here, for instance, which is supposed to balance this pole, we're going to see, does it do the job or does it not? And then more often than not, we will find that, the first design is not fine. And then we kind of look at what do we see in the experiment, and try to update our parameters by hand or manually. Now, this is of course very tedious and time consuming. So what we have been looking at and working with is to replace this basically with a database or machine learning based optimizer. And in particular, we've used Bayesian optimization, which essentially builds like a probabilistic surrogate model of this objective function of this J that you're trying to optimize. And this is obviously the function that you don't know, because this captures basically the dependence of the parameters, the dependence of the cost, like the performance that you care about on your parameters. And this you don't know because you don't have a precise understanding of the physical hardware. But Bayesian optimization essentially builds a probabilistic model of that function, and then it uses this to sample in a clever or in a systematic way. So, for instance, to maximize the information that you gain from an experiment. So let me show you how this works. So here is a video of one of our robots. This robot is now supposed to is learning to balance the stick in its hand. And what you see here is the outcome actually of a previous learning run. So you see here that the robot is doing this fairly well. But what we do now is we replace the short stick with the long one. Obviously, the dynamics are changing, and if we run the previous controller, the system goes unstable very quickly, so the robot is not able to solve the task. Now, what we do is we run our basically the Bayesian optimization approach on our controller architecture, and what you see here develop is this probabilistic model that kind of gathers the knowledge from the experimental data. So each of the points here is one experiment that we run on the left. And you see, and what we basically learn is this cost function, is the behavior between the parameters, this is the theta 1 and theta 2, to the cost. And we would like to achieve like a little small cost as possible to get, which corresponds to good balancing behavior. And what you notice here is that the system basically automatically, or the method automatically focuses on those regions that are interesting, while regions of high cost only get sampled very sparsely. So here we're using this machine learning model, this machine learning approach to basically sample very efficiently.
Okay, could I pause you, Sebastian, now
Absolutely.
to take questions, just to make this interactive, right? If you just, I know you may not get through all the material, but I have natural questions. I think everybody else does too.
Can you go back to the slide, the mathematics, the slide that showed the mathematics, please, Andreas? It's Andreas.
Yeah.
Let's see. I didn't show too much mathematics, but maybe
is
this one or this one?
Yeah, that. Yeah, okay.
Yeah.
I see. So do you run that in real time? You can.
No. So the way we do this here, and also the way I show this in the video, is basically you do one experiment, you gather the data, and you update your model, and you then propose a new experiment. Often what you can do then in an experiment is you do this in parallel. I mean, you get the data point, you then already run the next experiment while you compute, while you process your machine learning model, and then the next data point. But this is what I'm showing here is fundamental. It's like an offline approach. However, there's also ideas of how you can do Bayesian optimization online, basically also adapting with what the system is doing. But here, what I showed in this video is really an offline approach.
But can you show what J is on this J plot in 3D, right? What are the coordinates of this J plot, this theta 1? They're like the mass and the length or something of the model?
No, actually, so you mean here?
Yeah. What are the axes?
Yeah. So maybe it's actually let me go back then. I think we can best explain this here.
Yes.
So the theta really are the parameters of the controller architecture. So that's what I said, that basically when this approach,
like a proportional gain and derivative gain, for instance.
For instance, in this specific case, what I showed in the video, it's actually the weight matrix or entries of the weight matrices of the LQR of the optimal controller. So there's a cost. There's yet another cost function that we use to design the controller, and this one has parameters that we would typically tune and tweak by hand, and these ones are the ones that we now tune with Bayesian optimization.
But
and then you sample. Go ahead.
There. Looks like you only had 2 dimensions. So can you explain the relationship with?
Right.
Yeah. So in this video, I turn off the video optimization and can see you. So in this video, this was just 2 parameters of these, but you can also do more. So you typically often reach a limit, like when it comes to 10 or so. Then with these type of techniques, it gets more tricky. But basically, we there had 2 just for the sake of having a nice plot. But for the ADLQR problem, there really has something like 4 or 5 parameters that we would be tuning in parallel.
How about 1,000 parameters?
Yeah, not with those methods.
Not with those methods. So,
No.
okay, you want to talk about that?
I'm going to show an example where we have where we run a deep neural network as a controller, which in some sense has like that many parameters, but it's not this tuning problem. This is so here the philosophy is very different. Here the philosophy is very different from, you know, the deep learning type philosophy. Here the philosophy is, okay, we often know what a good controller architecture is. And in this case, for the balancing, it might be the LQR. In another case, it might be PID. We've also been tuning like observer-based structures where you have like some surrogate model that you use as an observer, and then you put a controller on top. But still there, you have some parameters of the model, of the plant model, or of the controller. And you can also tune these. So here the philosophy really is, let's use a well-established and well-understood control architecture that leaves you with only like 1 or 2 handful of parameters. And then let's tune these parameters with, in this case, Bayesian optimization in a systematic way. What do I mean by tuning in a systematic way? Systematic here in what I showed means information efficiency. So we sample where we believe to learn most about the system or most about the controller. I'm going to show, and just right after this, also how we can then combine this with the other data sources. But here it's information efficiency. There's other approaches using similar techniques that also would go for safety, where essentially you only sample where you already are relatively certain, so that you don't sample where there's lots of uncertainty. And this could also be, you know.
Could you illustrate by means of this 3D plot how the Bayes principle is working again? Is it really automatic, or you don't choose those points, right? The algorithm chooses on the next video, this nice video, no, not that one, the one that, that one, okay. In what way is it sampling those points?
Yeah, so so J is that's the cost, and now the cost is of 2 parameters, J of theta 1 and theta 2. Now, what you see here, this is basically the Gaussian process. More specifically, it's the mean. So the purple surface is the mean. This is kind of the expectation of how the algorithm thinks the functions looks like. And then you have the uncertainty, like these grayish areas. These are the uncertainty areas. And what this algorithm now does, it takes this probabilistic model and computes an information gain. Essentially, it asks, okay, if I'm going to sample anywhere in the theta space, what is the information that I'm going to gain? And an approximation, or like a simpler way of doing this, would be, to sample where the uncertainty is the largest. But here we have a combination of, it's not just the uncertainty plays into this, but then it's also that the algorithm knows that we want to optimize. So for instance, if I have a value that is already relatively high, then this is not very interesting for the algorithm, because it's very unlikely that the minimum is going to be there. While if you are somewhere that already has like a low mean, then this gives you an incentive to sample there, because the chances are higher that you find a good optimum. So maybe I run this again. So what you see here is that you sample in areas that tend to have kind of low function values, while those areas that give high values, so here, for instance, like maybe I can pause here again. So this area here has relatively high function values, and we have only sampled very sparsely here. So we have a few samples so that we see, okay, this is going up, and then we know, okay, this area is not interesting anymore. So we don't sample any further there. While this area over here tends to have small, low values, so we sample more over here. And this is what the algorithm gives you. So the algorithm automatically trades off this kind of, you want to go where there's uncertainty, but also where there's a good chance of finding a better optimum.
Any other questions?
Yes, but here you do not take any advantage that it was before able to stabilize it for a shorter pole. Yes, it actually doesn't matter for this example.
That's correct. For what I'm showing here, it basically starts from scratch. It starts from scratch. But what would also make a lot of sense here is to use. So it depends a bit. Like if you have that information available, and in this case we could measure like let's say the length of the pole or so, we could use this as a context variable, like an additional external variable in our model that we can use to basically correlate our model with let's say the length of the pole. And then next time, let's say we have a pole that is similar to one that we've already seen, we could leverage that information. But we're not doing this here.
Thank you.
Okay, thanks.
Sounds good. Then let me move on. Actually, so this connects right to what we talked about before, because now the core really of this approach is this probabilistic model. And what I've showed you and what we've discussed now is how can I use this probabilistic model to decide where I want to sample next, where I want to get more information. But we can also use this probabilistic model to now fuse information. And one typical thing that you will have in control or robotics or wherever is that you have the experiment, but you also have a simulator. And then the simulator does give you information, but it's less informative in the sense that it's only an approximation of the truth. But it's often faster, so you can sample fast. You can run more experiments faster. So then the trade-off or the question is, do I rather do kind of many less informative experiments, or do I do a few, more expensive experiments that give me more information? So do I do many simulations, or do I do physical experiments? And what is now nice about this probabilistic model is that this can also be used now to trade this off, because essentially you need to model like how much information do you get from each of these sources, and then the model can ask not only where do I want to sample, but also do I want to do a sample in simulation or in the experiment? And then I can compare basically the information gain that I get per unit of cost. And the unit of cost could be, for instance, the time that it takes to run such an experiment. And on a high level, this is what we're essentially doing now. The Bayesian optimizer not only says what parameters are we trying to do we want to try, but also do I want to try this parameter in simulation or in reality. So let me show you how this looks like on a video. So this is a simpler system here. So this is just a card pole, and we have like an experiment card pole and a simulator. And here the simulation is just a linear one, so it's really fast. And now we essentially run our algorithm as before. Let me pause this here for a second and then explain. So again, we have like two parameters. We have parameter 1, parameter 2. These are just two parameters, so similar to the ones before. And now we have the cost function here, also similar to as before. But now we have two options of doing experiments. One is to run a simulation. This is going to be a blue dot, or in red to do a physical experiment. And what we now see here as this evolves is that the algorithm decides first to do simulations. And then here it did one experiment, and it noticed, actually the cost values are actually higher than what I thought. So then it leaves this area. Then it continues with simulations and so on and so forth. And later on, it does a few more physical experiments.
Why did it choose that? Why did it choose that red point way to the right? Was that just a random choice? Is it stochastic, right?
Yeah, it's a good question. So I can't really pinpoint to, okay, this exactly is the reason why we chose this point. What we optimize here is the information gain, and we compare the information gain from a simulation and from an experiment. So there's many things that go into this. In addition, there's also a random component in there. But in principle, what this algorithm does, it compares the information gain that we get from the two. And then here it apparently decided to do one experiment there. Could have also been random here, this one, I don't know. But then what we do see is that because we go up high here with our cost, this area is not very interesting, and we don't do any further samples here. While this area here, we end up doing more physical experiments or samples, because this is also, I think, the area where we in the end find the optimal controller.
Can I ask a question of clarification? Just so I understand. The cost here is basically the control performance. In other words, how stable is the pole and how much effort. It's some measure that you've made up to measure how good it's performing, right?
Exactly.
In the experiment. So it's something that you measure by doing a control and measuring numerically what this cost is.
So
correct?
Specifically, it's a classical quadratic cost that combines quadratic weights on the states and the inputs you.
Yeah, but you measure it numerically by doing the experiment, either in simulation or reality.
Exactly.
Okay. But then in order to evaluate this Bayesian expression, you need to have the explicit controller, right? This wouldn't be appropriate for MPC or something, would it? it would be appropriate when you can evaluate this quadratic cost. The cost you can evaluate anytime, right?
Exactly. I mean, it would be actually. So I'm not showing any experiments of this, and but there's other groups that use Bayesian optimization for MPC. That's actually fine. So it doesn't really matter because as long as you can run your controller, either in simulation or in the experiment, then you're good, right? Because then you get the data.
But don't you need the marginals, like the derivatives, in order to evaluate these Bayes formulas?
No.
Or
no, actually, okay. So this is really just on. I mean, we built a surrogate model. This is then a Gaussian process that we use to do all the processing, basically. But we don't need a derivative or anything from a controller. So what we really, the sampling is just zero orders. You need zero order samples. You evaluate you run your experiment, and that gives you data point.
Thank you. Any other question? Okay. Go ahead.
And let me I continue this video. So so after just basically just the result of that tuning, in the end we have this the learned controller, and in this case we could save quite a few real experiments.
Rock solid. Yeah.
So here's another. Sorry.
So for CardPol, it was still LQR, tuning LQR, or was it something more complex?
Can you say the question again?
Yes, but for the controller you were tuning for LQR, it was just like for CardPol, it was LQR, or it was something else?
No, this was LQR. Yeah, this was again LQR. It's similar to the previous one. But here now combining the simulation with the real experiments.
Okay.
Yeah. So here's another variant of that way of doing tuning, which is where we also want to include failures in our experiments that we may have in our experiments. So let me show you or run this video and to motivate this a little bit. So what we have here is this quadruped robot, and we want to learn actually this robot to jump as high as possible. And jumping higher requires kind of more current, obviously, but then when the current goes too large, then the models shut off, and then you get failure. How it could look like, you have, the models shut off in midair, and then the robot falls over. So what we are looking at here is that basically we want to, I'll pause this here for a second. We want to we have a cost function. In this case, it's not the quadratic cost, it's more direct. It's kind of, we want to maximize the height. We want this robot to jump up as high as possible. But we now have a constraint, and the constraint is that the current cannot be too high. However, what is too high, we don't really know, because this depends very much on the physical representation of that robot. It might also depend on the specific controller that we use. Simply, what we know is that at some point the motors will shut off if the current ends up being too high. But the connection between our controller parameters and then the question like, when is the current too high? This is what we don't know. So what we have, or the way we model this, is that we say we have a constraint that depends on our parameters, the controller parameters, but we don't know what this threshold is. And now what we are doing is we want to kind of do two things. We want to learn, optimize the height, while also, learning the threshold on the side. Plus, when we happen to have a failure, because that could obviously happen if we don't know the constraint a priori, we cannot, put it into our optimization. So we might end up having a failure. And then we want to use the information from that failure. And this information from the failure is then basically, it's in a sense it's hybrid type of information, because if you run an experiment, and you can measure the height, and then okay, I can give a number. I can give a number of how well I've done. However, if I have a failure, then it just means, okay, I failed. I can't really give like a number. What does it mean? Does it mean I didn't jump at all, or should I give a penalty, or what should I do? So I really have this hybrid information that if I'm successful, I can assign a number to how successful I was. While if I fail, all I know is I failed. So I did worse than anything else that I've seen. And this is what we now we're doing two things here in this work: is we're learning this threshold, and we are we have modified model, a modified probabilistic model that allows us to include this hybrid information. So maybe I just run the video to show what now happens. So as I said, basically what we want to do, there's two things. We want to include this hybrid information from failure or success, and we want to learn this threshold. So let's now have a look at this robot. So here's now a typical run. So we start with an initial parameterization. It's doing okay. It's not really jumping very high. It's poor performance, but it doesn't fail. Then we keep going. Again, the objective is to maximize the information. So we kind of quite quickly get to reasonable heights. But then as we keep going, also it's a random exploration process to some extent. We happen to have a failure. Like this was a failure. But then we can now incorporate this information from our failure. One, to know, okay, here we didn't get a good performance, but also to get an idea of what the threshold is like. And then we keep going. Combining either success or failure, and in the end, basically arrive at a good controller. So I think we stop here after 50 iterations, and then we can compare like what we've achieved. So on the left is the initial one, the middle is like what we tuned by hand. These are all the kind of the best controllers. This is the comparison of 3 of the runs. And now we do the performance comparison. Like on the left is the initial one, the middle is kind of manual tuning, and then the Bayesian optimization framework in here achieved the best height.
So can I ask you a question of clarification here? Is it doing control during the jumping and during the landing to try to stabilize its landing?
No, well, okay. So that's a good question. So we don't stabilize the flight or the landing, let's say. So what we have here is we have controllers in those legs that basically control like the movement of the legs, and those controllers have some parameters, and these parameters we are tuning. So we're not specifically controlling, let's say, the flight or the landing phase.
Okay, so you just want to jump as high, and when it lands, it's done by some torque control or something like that happens to absorb the force. You don't concern with the landing at all.
Exactly. Yeah, exactly.
Okay.
Okay. Good. So that's actually the first kind of set of methods that I wanted to talk about. I was talking about like which is kind of Bayesian optimization for controller tuning, because the question was also for this talk, like what methods work, like from experience, like what methods work well, and I would say these are things that can work quite successfully. That if you have like a good controller structure, but then you want to offload the tuning of the parameters to a machine learning method, and then this machine learning method you can do to do different types of tuning. You can go for information efficiency, you can incorporate information from different sources, you can also do safe tuning, which is something that I haven't shown here, but you could also use that. So these things are, I would say often work quite well, and we've run this on several systems also with industry partners and so on. So this is something that in my opinion works very well. I want to show you a little bit like a slightly different perspective on in some sense the same problem, where we want to basically also find a good controller, but as we do this, we learn a dynamics model on the side, and this actually often allows us to be even more sample efficient. So let me explain what we do here. So the base question is the same. You want to learn a controller from data by interacting with the physical system. Now, instead of directly observing the performance on the platform and then tuning the controllers, we take a step in between here. We use the data, the input-output data of the physical plant, and to build a dynamical system model. And here we again work with a probabilistic model, so it's going to be again a Gaussian process. Which we then use basically for optimization. So we then optimize our controller parameters in an offline optimization procedure. And then once we have a new controller, we go out and do another experiment. Now this is the core framework of model-based reinforcement learning. Why model-based? Not because you have a model in the first place, but because you learn a model on the side. And why is this good? So if you manage to do this, if you get a good probabilistic system model here, then in a sense, you are done, because you no longer need to sample your physical system, because then you can do your optimization based on the model. But then the critical bit, of course, is how do you get this this probabilistic model in a nice way or in a reliable way. And this is, I'm not going to go, I don't have time to go into details here, but this is where we've done some contributions in this work, not the model-based reinforcement learning framework itself. There we used existing methods, but we've improved basically the way that these models are being learned, such that you get reliable probabilistic models of these. And just to compare to what we've done before, so we have the same task here. This robot is supposed to, let me optimize video clip quality again, and then I restart this. So this robot here is again to learn this balancing this stick. Now it starts without anything. It doesn't even have, I mean, there is a PID controller, but it doesn't start with one that is kind of okay with balancing. What we start here with, we just apply some random action, and from this random action, in the first iteration, the robot gets a first rough model, then it uses this rough model to update its controller, and then it does another experiment. So you see here, after 4 iterations, it almost got it, but not quite. And then after 5 iterations, it finally managed to balance this pole. And the interaction time with the system here is less than 20 seconds, which is way less than what we had to do with the Bayesian optimization approach. Because here we could use the data to train a dynamics model, which we then use for the optimization. And if this works, if the model converges, then you are typically more sample efficient. But of course, the critical bit is to get the model training to work. And this is what we've done in this work, is that we basically we proposed a new way of training these Gaussian process models. So we call this multi-step Gaussian process, MSGP, because it optimizes for more long-term ahead prediction, which is obviously critical when you tune the controllers. And then what we obtained in these experiments is that basically with the standard approach, which would be the green one here, in this example would not converge. So this is the loss over learning iterations. So one learning iteration means a new model and a new controller. And if we use the standard approach, the green one would never converge. It doesn't find a controller that would balance our task here. While with this other way of training the model, we were able to converge very reliably. So I think these are 5 learning runs, and each time we converged after 7 or 8 iterations. And this shows that quite obviously in the model-based reinforcement learning approach, the critical bit is to learn a good model. And then if you manage to do this, then you can be more sample efficient.
Yeah. Looks really practical. It looks quite practical. I mean, I'm curious if there are questions here. I think that people don't have much expertise here in Gaussian process modeling. At least I certainly don't. Maybe some people, we heard the talk, one of the first talks we had from Ugo Rosolia does heavy-duty Gaussian process modeling for, driving. Mm-hmm. And very successfully showed that he could use Gaussian process modeling to quickly learn with a couple of circuits of the track how to drive a car at the traction limits. A physical car, like an automotive car, the traction limits. Yeah, like this. I guess you've also done similar work, right?
So this is obviously not a real car. It's a model car. But this does also, it learns part of a track with the Gaussian process dynamics model, and then we use this to optimize a controller. So we did this in I think 2017 or so together with Bosch, and this worked quite successfully. That you use this GP dynamics model to get a good understanding of what the car does, and then in particular in situations like going around a curve or something where you want to reach the dynamics limits, and then you can use this to further optimize your controller.
And if you just pause this lovely video here, this is also very convincing. If you pause this video, this looks a lot like the rollouts that we're doing in our topic area. I don't know if Flo is there or anybody working on the L2 race. These are rollouts, right, of the Gaussian process model?
Yes.
From a particular point.
Yeah. So the Gaussian process model basically captures, from one state to the next state, and then you can unroll this, and this is what gives you those trajectories here. So let me run this again. So in the beginning, so here you see, there's also these uncertainty funnels here around, and as you gather more data, the uncertainty is basically reduced. So if I run this, these uncertainty areas shrink, and this is unrolling the GP model, and it gives you basically part of that trajectory.
It really seems quite practical. I mean, what is the problem with these Gaussian process models, besides the fact that they are assuming Gaussian noise or Gaussian uncertainty, right? If you have a bimodal, it doesn't work, right? If, for example, in some situation, you might have a bimodal distribution of uncertainty.
Yeah. So first of all, exactly. So first of all, the Gaussian process itself is just a nonlinear function approximator. So you can in a sense approximate any nonlinear function. That function, however, would be the dynamics function. So it would be state at the state at time t to the state at time t+1. And then when you unroll this, you typically also make a Gaussian approximation in between. Like obviously, if you start with the Gaussian, you push this through a nonlinear function, then you won't have a Gaussian. So if you want to keep this tractable, then what this method does and what these plots show is that you indeed that you then approximate after each step with the Gaussian again. And this, of course, as you said, this won't work if you have a multimodal distribution for your state, for instance. Also, Gaussian processes tend to, they're computationally somewhat expensive, or they have a problem when it comes to like really huge data sets, like large data size, big data size.
Well, that opens up the question. I mean, is it something that us hardware developers could think about accelerating, since Gaussian process modeling is so useful and so data efficient?
So. Because we're Monte Carlo, Markov chain Monte Carlo.
Sorry, I didn't acoustically understand here.
Markov chain Monte Carlo.
Yeah.
I mean, if you can do it in real time and fast enough, then you're in good business.
So I understood Markov chain Monte Carlo, but what
I mean, I think to accelerate stochastic processing of this sort, what do you need to have? I mean, at the limit.
Yeah, well, I mean, so one aspect. I mean, if you want to solve the full inference, basically this scales poorly with the number of data points. Yes. So one aspect one aspect to approach this is that you use sparse approximations where you approximate basically the full data set with a representative number of data points, and this way you can get around of also being able to handle larger data sets because you replace with a smaller number of representative points. This is one way how to approach it. But yeah, it depends what you want to do, I guess.
Just relating to being unimodal, in the plot we see multiple different trajectories. What does that mean with respect to the Gaussian process?
The plot that I'm showing here in this.
Yeah. So you get these different scenarios, but intuitively I would expect the Gaussian process here to have a single mode. So what creates these different?
I think those are different control inputs and the predictions. Now these are different measurements. And predictions.
In a sense, so it's different parts of the track, actually, of the racetrack. So it's different part of the racetrack, but it's basically predictions with the same Gaussian process model. But it's just different parts of the racetrack put in one plot so that we can see it all together.
Oh, I see.
But it's basically just different parts of that overall racetrack, because in the end, you want to be able to predict all parts of the racetrack well.
Thank you.
One thing I'm interested in, since you worked a lot with Gaussian processes, how difficult do you find it to tune the kernel functions, or how do you fit those? I mean, they're not fitted, right? They're tuned. So how difficult is it to do that for realistic systems?
So it depends. So you're saying they're not fitted, they're tuned. I think you can do both. I mean, it depends. So also often basically the parameters, the hyperparameters of the Gaussian process are optimized from data. Using hyperparameters, some form of hyperparameter optimization, but you can also tune them. It depends. I would say primarily depends on the data regime. If we are in really low data regimes, not so much this one that I showed here, but with the Bayesian optimization before, we really in the end have just like 10, 20 samples. You cannot expect that from that few samples you can actually optimize also the hyperparameters from data. That's not a well-posed problem. So there often there's different things you can do. One thing is that yes, you tune it by hand. You might know something. I mean, often, operators of a controller will know, okay, the parameters are in a specific range, and then roughly how they change. This is one thing you could do. You could also think about using the data from previous trials. Like obviously you don't want to rely specifically on the data of a previous tuning run, but you can use this data to basically obtain hyperpriors. So this would be prior distributions for your hyperparameters. And if you and these you could then use to basically start the specific tuning experiment from an informed state, that okay, roughly from previous tuning runs, this is what I can expect. These are length scales or orders of magnitude for my controller, and then you give this as prior information to the Gaussian process. This is something that you can also do if you have lots of data. And I believe in this application we just did standard hyperparameter optimization, where you basically also optimize the parameters of the kernel from data.
Okay, yeah. I guess it's something you have to just take into account, right? It's maybe a disadvantage of that method, but I guess if you have working strategies to counter it, it's okay. Because I would have another question going from there. I mean, do you think that any model kind that's not uncertainty aware has any justification in this kind of application scenario? Because you heavily rely on this being able to quantify the uncertainty of predictions, right? Do you think there is any justification to say, yeah, we can take a model that does not have any measurement of uncertainty of its predictions?
Okay, so there's a couple of things. First, you said basically it's a disadvantage that we have those hyperparameters. Well, I would say, you have them in any machine learning model. You have some hyperparameters, and then of course it depends. It depends on the application whether the hyperparameters are more easy or not to tune, let's say, or to obtain. But I wouldn't say it's specifically a disadvantage of Gaussian processes, because you will have other hyperparameters and other machine learning methods often or usually. Now, is a method that does not capture uncertainty justified or not? Well, I mean, it depends, right? I mean, if you want or need to have the uncertainty represented in your model, then you need an uncertainty model. But if it's like here, we use the uncertainty to basically here we use the uncertainty to get an idea of how precise are we in certain parts of the racetrack. And now this uncertainty, and I haven't shown this, but in other works we use this uncertainty, for example, to choose informed samples, to then decide, oh, now we need to have more data in this area because we have larger uncertainty there. And if you don't have that, then there would be no way that you can do this in informed sampling, let's say. But if it's just about the tuning of the nominal state, let's say, and you don't care about safety or anything, I think it's also obviously fine to use methods that don't have this uncertainty. Or you put other safety mechanisms around, like, I don't know if we still have time, but I could show another video where we use a deep neural network.
Please show one more video, yeah.
To approximate a model predictive controller, actually. And there we have like some basically validation procedure around. And the deep neural network doesn't have any uncertainty in there, but we have a validation that we put around. So do we have 5 minutes? And I can still show that. Okay, sounds good. Then so in what we are looking at here is in a sense a different way to combine machine learning and control. Like in this case, we assume we have a model predictive controller we start with, and this one we want to approximate. So why would you do this? First of all, well, why you would want to do is that because MPC, because it has an online optimization in each time.
You don't need to tell us. We know why. Yeah, just go ahead. Yeah,
I will. And therefore, what we do here is that we basically use the MPC to generate samples. So we have an MPC, but we run it offline to generate samples, and then we train a neural network with this. And if you do this, and that's obviously not new, people have done that before. But what happens if you do it just in a naive way? You lose the guarantees. Like the MPC comes with nice guarantees, but if you just approximate with the neural network, then you don't have these guarantees anymore. So and this is what we are looking at here. So what we are trying to do here, or what we're doing, is that we combine now a robust design on the control side that includes additional, uncertainty, and then we combine this with statistical validation on the machine learning side. So more specifically, what do? We assume that we have some additional hypothetical disturbance on our input. And then we design the controller such that it is robust, so it's stable no matter what this input is, or this disturbance is, as long as it's bounded. And then we use this to train our neural network. And afterwards, we run a statistical validation. So we run many samples and check what is the difference between the output of the neural network and the output of the MPC. And if, for many samples, the difference between is less than this D max, so we can validate with high probability that this property holds. Then, because we have the robustness property over here, we can basically obtain, or we retain the guarantees of the model predictive controller also for the neural network, because we know that these guarantees will also hold even if we have a little uncertainty, and we have shown with high probability that the uncertainty is actually within those bounds. So then you have the advantages of the neural network controller plus also the guarantees, however, in a statistical sense. And this is what I meant. Now, the neural network of itself is just a deterministic model, but we have these guarantees through the validation procedure around it.
What can it do?
Pardon me, what did you say?
Go ahead. Yeah, go ahead.
I was so what we see here in this video is now the robot that is supposed to basically reach to where we point with the stick. And on the left, you see just the robust model predictive controller. It's nonlinear robust model predictive control, and you see it's doing the job. You can also move around obstacles, but it is fairly slow. And then on the right, we have basically the same controller, but now approximated with the deep neural network. And you can hopefully see that basically the arm reacts much faster than on the left side. So on the left side, the arm is still reacting relatively slow. Here it's much faster on the right. So we're roughly 20 times faster than with the nonlinear MPC on the left. Now you also probably noticed that we don't move any obstacles through the scene here, because we really reached the limit of what we could sample with the statistical validation technique. This is at the moment the limitation. That if we go to higher problems, or like higher dimensional problems, you need basically way too many samples. But I should say that the way we do the statistical validation is also quite naive, and there's several ways that we think we can improve it. But this is kind of work in progress. But what this does show is that you can now run this deep neural network as a controller. It's much faster than the MPC, and we have guarantees at least for like reasonable or smaller sized problems.
What's the structure of that neural network controller? Is it an MLP that maps basically from? How does it?
So this is actually just a relatively standard feed-forward neural networks. Feed-forward neural network. I think it's primarily using ReLU activations, because it's really just a classical supervised learning problem that we're solving here. We have just some input states, and what we get is the control inputs, and this is just what we are mapping. So there's nothing fancy in terms of the architecture.
Yeah, no, but it's able to control all the degrees of freedom and do the feedback control, right, for stability, stable control, right?
So it does the feedback control, yeah. But if you think about it, I mean, the MPC, the MPC at the end of the day it's a map from, you have a state, and this state gives you an input. So it's a map from X to U. So it's just this, and if you have many samples of these, it's just a supervised learning problem. Now, what you're saying makes a lot of sense. So this is another direction we want to extend this, because often in MPC, we know there's areas where, for instance, you have, you clip your inputs, right? I mean, you're operating at the limitation of your inputs. So this is like, these type of things would make sense to somehow incorporate in the neural network architecture, so that you don't have to learn that from scratch.
So I have a comment on, which is really, you address now the computational complexity. I mean, the problem is still a cubic complexity. It has cubic computational complexity, because that's really what you have in a Gaussian, when you're using Gaussian process to do.
This is not Gaussian process modeling, though, right?
This is not Gaussian process.
Yeah. So how many, I mean, again, what's the limit of doing this in real time with how many parameters? I think that's a question that Toby was trying to ask earlier.
No, it's not. I was just asking about this particular neural network control, which we're trying to avoid, right? Because we realize that nobody will accept a publication with a neural network controller unless you can make some kind of safety guarantee, right? Is that true, Sebastian, in your experience, just for this community? In the control community, it's difficult.
Depends on the community. I mean, there's lots of controllers, neural network controllers that are proposed in deep reinforcement learning that are used that don't have a safety guarantee. Whether this is good, I think is questionable. I think it's good to push on both ends. I mean, you want to push on the performance side. You want to show what is possible with neural networks, with deep neural networks, even if you don't in the first place have a guarantee. Obviously, you can only use this for a very limited number of applications then, but and at the same time, you want to push like, how can we reach safety guarantees, right? And here we are more on kind of how this is an approach of how we can get some safety guarantees for the deep neural network control. And just to emphasize, this is not a Gaussian process, this is a neural network. But the limitation really here is the number of samples that we need for the statistical validation to get reasonable safety guarantees here. But I think, I mean, there's definitely, I mean, if in deep reinforcement learning community, I mean, what people do is they train neural networks, deep neural networks for control tasks, for robot manipulation tasks or other tasks. And there's not that each of these has a theoretical guarantee.
Thank you. Okay, so sorry, but we're out of time. I want to give you a great big thanks, and also for being so patient with the typical Telluride technique of interrupting you and derailing your presentation at the very beginning.
No, this is perfect. I appreciate it. I appreciate the discussion. Thank you.
The talk should be driven by the audience, or more of the audience than me, right? Basically, you get pushed around, right? So your talk is totally different than what you thought it would be.
Yeah.
So anyway, thank you so very much. It's really appreciated, and we would appreciate also your advice within the topic area in terms of practical experiments that we could carry out as in projects. If you're willing to join us an hour from now,
sure,
we really appreciate it.
Sounds good. Yeah, thanks a lot for having me. My pleasure.
Thank you. Okay, in that case, I'll stop the recording now because I think we now have just a topic area meeting. Is that true, Emre?